All right, welcome back, Physics 12, to your lesson for the week of April 14th to April 17th. Today we're going to be learning about electric potential, and we're going to see how it relates to potential energy, and we're also going to see how it relates to fields. So the first thing to do is recall what the unit is for potential. So if we go back to our square, just as a quick revision, we've got potential energy, and then on the bottom we have fields and force, and these ones are both going to be, if we're talking about point charges, they'll be over r, and this will be over r squared. These will be q, and these two on the right would be q1, q2. So if we want to go from fields to force, or from potential to potential energy, we would need to multiply by Q, and likewise, if we're going to go from energy to potential, we would need to divide by Q. So in other words, field is how much force there is per charge, and potential is how much energy there's going to be per charge, or divided by charge. And then, just as a quick review again, to go from force to work done, or change in potential energy, we know that we're going to have to multiply by distance, or r. Again, distance is going to be if we're talking about parallel field lines, and r would be if we're talking about point charges, which we'll go into more detail on in a week or two. So that's our relationship between these four quantities. So again, if we want to know what the unit is for potential, well, the unit and the formula is going to be determined as follows. V, or potential, is going to be the potential energy divided by Q. So take energy, divide by Q, and that gets you to V. And if we want to know the units, well, the units are going to be the same unit as the formula is going to indicate. So potential is energy per charge, which means it's going to be how many joules there are of energy for every coulomb of charge. So that's our unit, and that's our formula. And we can define electric potential as follows. We can say that it's the work done per unit of charge in moving a positive, ran out of room there, moving a positive charge from infinity to a point. So when we looked at potential gravitational energy, we defined it as being zero at infinity. So we know that everything is with gravity, everything is attractive. So I'm just going to make some notes on the side here for you. So with gravity, let's say we have a planet here. If I put a mass here, the gravitational force is always going to be an attractive force. It's always going to move towards there. So when we did our graph of potential energy versus distance, it was zero at infinity, and it would be kind of asymptotically moving this way, and then go down asymptotically this way. So this is what our potential energy graph looked like, and so it was zero, and it would always be less potential energy as it moved closer to the Earth. That makes sense. If we take an object that's on the top shelf and we move it down to the bottom shelf, we reduce the energy. Likewise, when we move something closer to the Earth, in this case, we're reducing the energy. The difference being is that we define our 0 point to be at infinity. Now, when we're dealing with potential, by default we deal with positive charges for kind of everything. So when we have a positive charge here, we would draw the field lines going away from it, because we're saying what is going to be the direction of force on a positive charge. So if I put another positive charge right here, it's going to be moving in this direction. So what I'm getting at here is that how we define this is how much energy it's going to take to move a positive charge from infinity to this charge. So let's say I've got a tiny little positive charge here, and I want to move it towards this charge here, this main charge here, and this is just a tiny positive test charge over here, well, we're going to have to do work because we know the positives are going to repel. So if I want to take this charge and bring it closer, well, that means that I'm going to have to be applying a force in this distance, so I'm going to have to do work. And so when I push this towards here, it's kind of like lifting it up a hill. It's going to get more and more and more and more and more potential energy as it gets closer and closer to here. So as I take it from infinity to here, it's going to gain potential energy. And we know that because if suddenly I were to release it, if I brought this charge from an infinite distance, brought it really close to here, and then I released it, well, we know it's going to immediately fly away again. So it has potential energy because if I release it, it's going to immediately change that to kinetic energy. So hopefully that makes sense. So that's where this definition comes from. Work done, the amount of work that I have to do to take a positive charge from infinity to the point. And so around a positive charge, it will be a positive potential, and so positive charge, positive potential, and likewise a negative charge is going to have a negative potential. So positive charge, positive potential, negative charge, negative potential. We'll see that a bit more detail in just a second here. And just like with potential energy with gravity, we define zero potential energy to be at infinity. So when it's an infinite distance away, there's no potential energy. And as it gets closer, if it gets closer to a positive charge, it's going to have more potential energy. And as it gets closer and closer to a negative charge, it's going to have less potential energy or more kinetic energy. Okay, so let's make another comparison to hopefully improve your understanding a bit. So since gravitational potential energy depends on height or elevation, lines of equal height would be called gravitational equipotentials. So it's a big word there, gravitational equipotentials. So if you made a map of this would essentially be a topographical map. And so a topographical map shows equally spaced lines of constant elevation. So what we're saying here, if you've ever seen a map like this is a bird's eye view of, say, a couple of mountains. You've got a mountain ridge over here, and then you've got a mountain peak over here. These lines might represent the height. This is 100 meters, 90 meters, 80 meters, etc. So something to think about is, although this is saying it's 100 meters, 90 meters, etc., this could also be a measurement of the potential. So this could say that we're going to have 100 joules of energy for every kilogram that I put here. Likewise, 90 joules of energy per kilogram, 80 joules of energy per kilogram, etc. So a map of height and a map of potential would look the same. They would just have, the numbers would be scaled by, one would be 9.8 times bigger essentially. So in this, so don't worry too much about the numbers specifically what they're saying, but in this case here, higher number would mean a higher altitude, but we also know a higher altitude would obviously mean you have more potential energy. And if you have more potential energy, it's also fair to say that you're going to have more potential energy per kilogram, or every kilogram that you have up here is going to have more potential energy than a kilogram that you put down here. So this could be a map of height, it could be a map of potential energy, it could be a map of just potential, or how much potential energy there would be for every unit or for every kilogram of mass. So where the lines, if we look here on this map, where the lines are closely spaced, the elevation is changing more rapidly. Now, if you compare these two maps, this is a top-down view. This top one here is a bird's eye view. You're seeing it from above. And if you look at this line here, A to B, this is what we're seeing here. So A is going to be this point on the map here. B is going to be this point along this line. So this corresponds to the valley right here. This corresponds to the peak. This corresponds to this peak here. And you can see in this general region here, the lines are very close together. And you can see in this general region here, it's very steep, right? Because you're going from, over a very small distance from here to here, so we've maybe moved 100 feet to the right or 30 meters to the right, but at that same time we've gone up by from 70 up to 90 meters. So we've gained quite a bit of height in a short amount of horizontal distance. Whereas here the lines are quite far apart, which means you've dropped 20 meters, but over a very long horizontal distance. So this is going to be less steep, and this would be more steep here. So when the elevation is changing more rapidly, essentially we're saying it's steeper terrain. So the terrain is steep. And so at this point here, our resultant force, our overall force, would be larger here. And it's also, just as another point here, it is going to be perpendicular to the equipotentials. Or to the equipotential lines. And the reason why I say the force is going to be greater, well, if you were to roll a ball down this part, you would have an overall resultant force that was quite large. You would obviously see this ball accelerating in this direction very, very quickly. Large acceleration means that it must have a larger overall force. If you were to drop that same ball from this point here, the acceleration would obviously be quite a bit less. So the resultant force would be quite low, and we know that because the resultant acceleration would be quite low. Here, the resultant force would be quite high, and that's because we know that because the resultant acceleration is quite high. Okay, that also means, so if the force is greater, that must also mean that the field is greater. Because field is just how many newtons we're going to have for every kilogram. So if I put a 1 kilogram ball here, it's going to move, essentially the amount of force that each kilogram is going to feel is going to be the same. Whether I put a 1 kilogram or a 10 kilogram, the field strength will be constant. It's going to give us a certain overall force. Let's say at this point, it's not quite 9.8 newtons per kilogram, because there's a bit of an angle here, but it might be, say, 8 newtons per kilogram as the overall field strength, or the overall kind of acceleration down the hill. So the field is going to be greater, and also the field lines are going to be same thing as we said up here, perpendicular to the, perpendicular to the equipotential lines. So let's take a look at what that means in depth here. So if I were to roll a ball here, let's say I dropped off a ball here, well, what would be the direction it would move? Well, it's going to move kind of the quickest path it can get to the 70 meters. If I'm looking at it from this side here, for example, it's not going to roll this way and kind of meander its way down the mountain. It's going to roll the quickest path it can to get downwards. And what that means is that it's going to always end up being perpendicular to the field line. So if I roll a ball down here, it would follow this path here. Likewise, if I rolled it here, it's going to move this way, maybe this way, something like that, right? But it's always going to be perpendicular to the field lines. That's the direction the ball is going to roll. So you can do that anywhere you want here, and it's always going to be the same result. It's always going to move perpendicular. Okay, so that's what that is saying there. The field lines are going to be perpendicular, and that's also going to be the direction of the force. It's going to be in the direction of the field lines. And the potential energy, I guess what I should say here is the change in potential energy is greatest when the lines are closer together. So the change is greatest when the equipotential lines are closest together. And hopefully that makes sense. You know, if I move this short distance, we've lost, say, 20 meters, so times 9.8, we're going to lose, for a 1 kilogram mass, we're going to lose approximately 200 joules of energy over this short distance. Here you're going to lose 200 joules of energy over a very large distance. So when they're closest together, you're going to lose the potential energy the quickest. And again, these lines, like we said here, they're called equipotential lines. So this is how we have compared gravity. And one more note here, if you move from one point on the map to another that has the same altitude, what would your change of energy be? So what that's saying is, if I were to move from, say, here over to here, what would be the difference in potential energy? And hopefully you can see, well, here my potential energy is going to be mgh, and here it's going to be mgh. And in both of those cases, the h is the same, the g is the same, and the m is the same. So when you move from one point to another along an equipotential line, you don't change any energy. So if you move from one point on the map to another point on the map that's at the same altitude, the change in potential energy or change in energy is going to be 0. Now, this leads us to a second point here, which is trying to figure out how much is the work done. So we know that the work is the change in energy. And the change in energy, if we go back to our square, if I want to go to work or change in potential, how do I relate that, or sorry, change in potential energy, how do I relate that to potential? Well, I'm going to need to take to my potential, multiply it by Q, and that's going to give me my potential energy. So this is going to be delta V times Q. So a nice shorthand way of solving the total amount of work done. Again, thinking about energy, how sometimes it's easier to solve an energy problem because you just need to have the starting position and final position. This is an example where it gets a lot easier. So if I want to know the work done or the change in potential energy, that's just going to be the change in potential multiplied by every amount of charge. So you can either write it this way, or you can write V final minus V initial multiplied by the charge. So if this, say, for example, is 80 joules per coulomb, and this is 60 joules per coulomb, well then there's a total potential difference of 20 joules per coulomb. So if I put a 1 coulomb charge going from here to here, that would be 20 joules of potential energy, either gained or lost, depending on the direction that it's flowing. Okay, and let's carry on from there. So hopefully this is making a bit of sense so far. So we kind of jumped from talking about this as a gravitational problem to talking about this as a potential problem. And if we're dealing with this as a potential problem, well, this would be an area of positive charge, and this would also be an area of positive charge. And we know that because it's going to have a positive potential nearby, which is kind of what we talked about over here. So the higher, the closer you go, the more potential you're going to have, or the more potential energy per charge you're going to have. Okay, let's carry on. So that first scenario there was looking at kind of a weird scenario. You might have a bunch of charges. You'd have to have really a bunch of charges in weird areas to create a map like this. It is possible to make a potential map like this, but most of the time you're going to see it kind of in one or two different scenarios. So one scenario might be a positive charge, and then the equipotential lines might be something like 100 joules per coulomb. This might be 80 joules per coulomb, etc., etc. So this is one way we're going to see it. The other way is looking at it as parallel lines. And so if we have two parallel plates, so I'm going to just delete this here. If we have two positive plates, in the real world that might look something like this. We have a positively charged plate and a negatively charged plate. And these two plates would create, there's two things that we can draw on here. So one of the things we can draw on here is the field lines, and we've discussed this already last class. The field lines are going to go from positive to negative. So this would be our field lines. But what would our potential lines look like? Okay, so let's try and make a comparison that compares the electrostatic potential to the gravitational potential. Now, one of the ways that we can do this is to visualize these parallel plates as sort of like a skateboard ramp. So I'm going to try my best to draw this out here. And so something like this. Okay, so this right here would be like our positive plate, and this right here would be our negative plate. So you can see here that the field lines would still be in the same direction here. The field lines would go from positive to negative. These represent the direction of force on a mass. If we're going back to gravitational potential, these red lines would represent the direction of force on a mass. But likewise, it would also represent the direction of force on a positive charge. If we're looking back to this comparison on the right, these field lines represent the direction of force that a positive charge would experience, and of course we know it would go away from the positive plate and towards the negative plate. So these field lines would all be pointing downwards. And likewise, if this was you're considering this as a positive charge, it would move down from positive to negative, or if you were considering this as a mass, it would move from the top of the ramp down to the bottom of the ramp. So just a nice comparison. Now, if we were going to draw equipotential lines, so lines where the potential energy was going to be the same for each, the gravitational potential energy would be the same for each unit of mass. Pause the video for a moment and try and think about how you would draw those equipotential lines. So you can think of this in terms of gravity, or you can think of this in terms of electrostatics. How would you draw lines on this graph that would represent areas of equal, or lines of equal potential energy? So pause the video now if you need to, and we'll come back in a second. Okay, so hopefully we can see here that if we were looking to draw equipotential lines, they wouldn't be those weird curvy lines that we saw in the previous part here, where there's a positive charge here and a positive charge here. They're going to be a little more symmetrical, obviously. And so in this case here, our equipotential lines would be like this. They would go, first of all, you can see they would go perpendicular to the field lines, and they would go parallel to the plates here. So anywhere along this blue line here, they're going to have the same amount of potential energy. So let's say the potential here is 100 joules. We can either say 100 joules per coulomb if we're thinking electrostatic, or we could think 100 joules per kilogram if we're thinking gravitational potential. So the top here might be 100 joules for every coulomb of charge, or 100 joules for every kilogram of mass. If you were going to go down to this line here, it might be 75 joules per kilogram, 50 joules per kilogram, 25, and 0 joules per kilogram, or per coulomb. Either way, the analogy works. So we can see as something rolls down, it's going to have less and less potential energy. And likewise, if you have a charge here, again, between the parallel plates, our equipotential lines will look something like this. So 100, we're going to call this volts if we're dealing with parallel plates. We're going to call this 100 volts, and 0 volts, again, we'd have 75, 50, 25 volts. So if I've got a positive charge here, it's going to have 75 joules of potential energy for every coulomb of charge that I put in here. So that's another thing to point out, just in terms of units. I don't know if I've mentioned this yet, but 1 joule per coulomb. The unit that we have for electrostatics is 1 volt. So this is essentially the same thing. 1 volt means that for every coulomb of charge, there will be 1 joule of potential energy. So if I were to put a 1 coulomb charge here, it would have 75 joules of energy, or we can say that at this point here, it's 75 volts. Both of those mean the same thing. Okay, and if we're talking about for fields, just taking it back to last week's lesson, we know that fields can either be the potential per distance or the force per coulomb of charge. So they can either be volts per meter, or they could be newtons per coulomb. So these are the two units for E right here. So electric field strength volts per meter or newtons per coulomb. So we could take a look at this if we knew the distance between here. So if we knew the distance between here and here, let's say the distance was 1 meter, well then in this case here the field strength would be 100 volts per meter. Or we could say the field strength is 100 newtons per coulomb. So volts per meter, newtons per coulomb, completely interchangeable. They're just telling you a different bit of information. So this is kind of indicating to us that here there would be 100, or anywhere along these field lines here, it would be a field strength of 100 newtons for every coulomb of charge. Or you could also say that there's going to be 100 volts for every meter. So both of those are the same number, it's just different units that can describe it in different scenarios. Okay, and importantly here, just an extra fact, the potential is going to be greatest at the positive plate. That's as high as it's going to get, is at that positive plate. Also, one thing to think about is the electric field strength is equal to the negative of the potential gradient. So if we were to look at this here with parallel plates, what do we notice that's different if we were going to compare this to, say, our analogy when we used a positive charge? So if we think about a positive charge just sitting in space, the potential around that, if we're comparing it to gravity, is going to look something like this. So we're going to have the equipotential lines would look something like this. And if you're looking at it from the top, you'd see this would be our positive charge and this would be our equipotential lines. If you're viewing this from the top down, it's going to look like this. So there's a positive charge and we have these equipotential lines that circle around it. Now, this is going to be, well, we know this from our formula for potential, this would be a 1 over r relationship. So that's the shape of this curve here is 1 over r, whereas you can see the shape of this is going to be it's linear drop off. So it's not going to be something where it falls off as 1 over r. It's going to fall off just as a linear relationship. And so in this case here, if we want to know what the field strength is, well, it's equal to, you can kind of ignore the negative for a moment there, that's not too important, but it's equal to the potential gradient. So you can kind of see here, if we compare these two scenarios, if we were to draw the gradient here, we would see it's a steep gradient, and over here, it's a less steep gradient. So this is telling us that if I were to put a positive charge here, there would be a huge amount of force because we have a very steep gradient. So that means we'd have a very strong field strength, and that means we'd have a strong force acting on this positive charge. Whereas over here, we have a lower gradient, which means we would have a lower field, which means the force on this would be weaker. And that hopefully makes sense. If you put two positive charges close together, there's a large force. If you put two positive charges a bit further apart, that force will be reduced. Now, pause the video in a second after I ask you this question. What does this tell us about the force acting on a particle if we are looking at these parallel plates? So how does the force compare at the top or the middle or the bottom of this ramp? Or likewise, how would the force compare if you're here or here or here or here? How would the force compare in parallel plate when we contrast that with the force here? So what's the relationship between your position in here and your force? So pause the video and try and think about that question for a moment. Okay, hopefully you're back and hopefully you have figured out that important bit of information, and that is this right here. So between parallel plates, the field and force are constant. So what I mean by that is we can see this first of all with the fields. If we look at these field lines, one of the ways that we measure field strength is how closely the lines are packed together. Now if we look at this diagram up here, does it seem at any point like the lines are getting closer or further apart? And the answer is no. These are all parallel lines. And so if the spacing between these field lines remains constant, that means that the field strength is also going to be constant. And if the field strength is constant, let's say 9 newtons per coulomb, then that's also going to mean that the force is going to be constant. So between parallel plates, the field and force are constant. Whereas next to a point charge, it's definitely not going to be constant. You'll have a greater force when you're close and a lesser force when you are further apart. Okay, and let's look at this one more time. But now let's pretend that these equipotential lines are not lines of equal altitude, but let's assume that they are lines of equal electric potential. So, what would our field lines look like here? Well, what we know is that our field lines are always going to be perpendicular to our potential lines. So we can see that in this diagram on the right, and we can also see that on this diagram here. This right here was my lines of equal potential. I know my field lines would look like this, and again, you'll notice these are always perpendicular. So that's just the way it's always going to be. Your field lines and your equipotential lines are perpendicular. So if I was going to choose a place on the map, like here, for example, it's going to go this way, this way, this way, this way, maybe something like that, right? It's not a perfect illustration, but it is always going to be perpendicular to these lines. There's a couple other examples there. Okay, now last bit I have for you is let's take a look at this potential graph. So if I have a point charge, so getting to what we were saying before, if I have a point charge, then this is going to be my potential on this graph. Let's say at the origin here, at this point, there's a positive charge, and this is a measurement of distance. Well, then our graph is going to look something like this. This is opposite of our gravitational potential graph that we would have drawn, because with gravity, it's always going to be attractive. So with gravity, it's always going to be negative. So I'm going to draw this here. This would be for a negative charge, and this would be for a positive charge at the origin. Positive charge potential is going to look like that. Negative charge, the potential is going to look like that. Same with gravity, because in the case of gravity, we're talking about a mass that's acting on something. So if I put a mass closer together, I know my potential, one mass closer to another mass, my potential is going to decrease. But in the case of electrostatics, we're dealing with a positive charge. So if I put a positive charge here, it's going to gain potential energy as I bring it closer. And if I put a positive charge here, or sorry, if this is a negative charge at the origin, and I put a positive charge here, it's going to lose potential and it's going to gain kinetic. Here is where we're going to see if I had a positive charge here, it would gain potential and lose kinetic. So if I rolled a ball, you can kind of imagine it as rolling a ball this way, it's going to gain more and more potential as it gets closer, and going to lose kinetic, and vice versa. So this is what it looks like if it's a positive charge, and this is what it looks like as a negative charge. And just to remind us of what we discussed above, the gradient here is going to tell us the field strength. So this line here, this is going to be our field strength. And so for example, the field strength closer to the object is going to be greater, which means there's going to be a greater force. So if this is a negative charge, then a positive charge would be attracted even more towards it. And if this is a positive charge, there would be an even greater amount of field strength, or a greater force pushing this other positive test charge over to the right. So a lot of content to cover in 1 week. One last thing I forgot to mention here, and this is how we measure energy when we're dealing with subatomic particles such as electrons. So in the case of particle physics, when we're talking about a particle accelerator, something that fires electrons, we have something similar to that at UBC Triumph or CERN in Switzerland. These are both particle accelerators. And so one of the units that particle accelerator scientists will use is something called an electron volt. So we know this E is going to be 1.6 times 10 to the negative 19 coulombs. So this is the charge of an electron. It can either be written as E, or sometimes it's written as QE. So Q with a subscript E, meaning the charge of an electron, or sometimes it's just written as E, an electron. And it has a certain amount of charge. And we also know that work done, as we saw earlier, work done is just our potential multiplied by Q. And so if we look at this unit for energy, the electron volt, what this is going to be is it's going to be 1 volt times the charge of an electron. So in other words, in terms of the energy, it's going to be 1 volt. And you can think of it this way, 1 volt is 1 joule per coulomb. We're going to multiply that by 1.6 times 10 to the negative 19 coulombs, and that's going to give us our answer. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So it's just a common unit that's used because sometimes they'll say an electron was fired between a potential difference of 2,000 volts. So we just take 2,000 electron volts. That's what it would be. One electron going between, let's say this is plus 2,000 and this is 0 volts. Well, an electron traveling from here to here, oh sorry, it should be the other way around. An electron traveling, as it's going to go towards the positive, so an electron traveling in this direction here would gain 2,000 electron volts, which you could then convert into joules. So sometimes you'll be able to answer it in electron volts, sometimes it'll ask you to find it in joules, but that would be how we would find that. So it's a very common unit. Some of the questions that I posted for you will have that as the answers or in the question. Please feel free to answer either in terms of electron volts or in terms of joules, your discretion, unless the question says otherwise. Okay, hopefully I have answered all your questions so far, but please feel free to join in next Wednesday at 10 o'clock when we're going to have our tutorial session or our YouTube live stream, and the link will be posted in Google Classroom. Okay, thanks and bye for now. Stay healthy.